Okay, so here we go. And please remember with this presentation again, like last time, I'm unable to see your chat box. So please continue putting the questions on the chat box, and we'll come back to it once the lecture is done. Okay, so I might take pauses in the middle, but yeah. So for now, we just begin with the topic. Uh, I'll just Before that, I'll just switch off my video so that your streaming is better. Okay, and yeah, here we go. Okay, so each one of you have experienced tensile structure in some form or the other, and I'm sure we it's very exciting to know what the tensile structure is about. It apparently it looks very simplistic. It's just like a fabric, and it's like a tent. Okay, but the structure or understanding the tensile structure requires a thought process which we have not conditioned you so far in these many years, in 5 years, okay, 4 years. So what is that? Basically, if we go through this presentation, we'll understand what are the fundamental differences and what is required to be done, even at a conceptual or the way we think of the structures. Okay. So a tensile structure is a structure in which every part of the structure that forms enclosure roof is loaded only in tension, with no requirement to resist compression or bending forces. Okay. It is very ideal when designer wishes to use minimum amount of materials for functional or aesthetical reasons. Now, if you look at all the other structures, buildings, which architects are, see, tents traditionally and historically, they have been in the domain of caravans and, all the nomadic tribals, they have built their tents, or these are simple structures or made up of fabric. But when it comes to architecture, architecture has always been associated with permanent forms. Okay, and tents or tensile structures have been associated with temporary forms. That's why for a long time, the tensile structures have not been so much of part of an architectural domain. But in the past, almost 50, 60 years, there has been a substantial development both in materials as well as the intent and the architect scope, which pushes us towards understanding this form of architecture as well. Okay, so and increasingly we combine these lightweight tensile structures or lightweight materials with the robust forms of the static build forms to come up with uh, designs which gives a certain lightness to the whole scheme. So tensile structures are broadly categorized into two. One is either they are membrane structures or they are cable net structure. Now, what does membrane structure mean? It's a thin, flexible surface structure that carries loads primarily through the development of tension stresses and acting simultaneously as structure and weather shield. It's like if you if you take a fabric, a chadar, okay, or your handkerchief, and stretch on all sides, that will be considered as a membrane structure. But if you look at a net, okay, or net with all the fibers, okay, the each strand of that net is a cable. Okay, so the difference is nothing but if it is a continuous membrane, a rubber sheet or a fabric, then it is considered as a membrane structure, whereas if it is made up of these reinforcement cables, and between that net you have panels associated, then these are cable net structures. So conceptually, in membrane structures, you have two types. One is tent structures and pneumatic structures. Obviously, pneumatic structures cannot be made up of fabric structures like cloth fabric, woven fabric structures. It has to be contiguous, like rubber sheet or PTFE sheets or any plastic sheets. So pneumatic structures have been in existence for the past almost 50, 60 years. But 10 structures have been in existence for for ages, for millennia. Okay. Cable net structures, conceptually they are similar, except that their surfaces are made from cable net meshes and carries non-structural layer of weather shielding elements such as acrylic, glass sheets, or wooden shingles, etc. Okay. Now let's see some examples. Examples of membrane structures is these. Obviously, there are some cables. I don't know. I'm not able to have hover a cursor around over here, so I'll go exit this. Maybe I'll view.
You can see your cursor. Now we can see all this.
Yeah,
So you can
yeah,
keep it
but
in this mode and go ahead.
I'm just removing this. Uh,
That side.
yeah.
But even if it's on be the slide is pretty much clear. Unless if there is written a lot of written material, then you may have to go into the full screen mode. Otherwise, images wise is not an issue.
Okay. Just checking out if there is. I want to remove the navigator.
Only the right hand block, if you can remove that would be nice. Right hand block. Otherwise, it's fine. You can continue.
Okay, I'll check it later, maybe. So
Vipul,
if you
you
look
can
at
do it from the first icon, which is there. That small square, it says hide the thumbnails. You can do it from there.
this one,
No,
so
no, on
right.
your left corner, left. The leftmost square. Yeah,
Ah,
that one. Yeah. Slide only
like
or
that.
something.
But then it's not giving me this, removing this part. Okay. Anyway, so if I get,
I think
that's fine.
using the cursor is more important because you can then
Yeah,
exactly pinpoint.
yeah,
That block B it's not an issue. Only when the write up comes, then perhaps you may
yeah.
want.
You can hide the right column from the view option, which is there on the top bar.
Which
There is,
one?
yeah, from view, there is view.
Of view.
File, edit, insert, slide, format, view.
Yeah.
Yeah. Um,
So navigator is on. Oh, yeah. No, not on. This is navigator, right?
yeah. You can do hide toolbar. Yeah.
Okay.
Hide
Slide.
tool. Down.
This high tool bar. Yeah. No, that is
Oh, it's not there.
okay. Anyway,
Yeah. All right.
not able to do that. Anyway, so what I was showing was this. So though like this portion of it can be considered as membrane, okay, but there is definitely a cable over here. But on the whole, this is a combination of cable, but it's not. Yeah. Hello.
Yeah, go ahead. We can hear you.
Okay. So, though these are cables, but this is not a cable net structure. I will come to, I'll show you what a cable net structure is. This will be classified as a membrane structure only, but with reinforcements. Okay. Then I'm not able to navigate. Great. Escape. Uh, okay. Okay. So in the where in the these are some more examples of membrane structures. So membrane structures need not be only the regular tent-like structures. They can be inverted umbrella-like structures also, as is seen in this Hajj. Uh, this is a beautiful structure in Hajj, and they can be collapsed. So the advantage of tensile structures is it is flexible, so it can open up, keep the space open, as well as it can be closed to give the sunshades. uh, why am I not able to navigate it further? Whereas this is the example of a cable net structure. Okay, now if you look at these, each one is a cable, and this is obviously concrete. There is concrete over here, and between these cables there are these glass pieces, which are glass panels, which form a continuous seamless thing. So even these are considered, these are tensile structures. Yeah. So you will realize that most of the time, or even in this case, so most of the time whenever somebody is making free forms, it is advantageous to use this combination or understanding of the tensile structures. Yeah. So tensile structures do not necessarily mean tents. Okay, they have variations. We will also talk about, this is irritating now. I'm not able to. Okay. Okay.
Good enough readable.
Okay. Thanks. Because I'm not able to navigate on that. So if you look at the characteristics of membrane structure, what are they? Their stretched surfaces tend to adapt their shape to the way they are loaded. Okay. They need to be stabilized to maintain their shape under variety of loading conditions. Now, this is very important, where if you just have a fabric, or if you just have a handkerchief, and if you don't pull all the four corners, okay, you're not going to get a stiffness. Okay. So similarly, in these tensile structures also, it is not enough to imagine that the object, now this is very different from when you place a block or a brick, one upon the other. So the brick itself, because of the inherent property of the brick, it has the ability to support itself, whereas a fabric does not have the capacity to support itself. So what you will need to do is you have to think about tensile structures both ways. So when they are loaded gravitationally, so the tensile structures, when they will have some gravitational load, but the gravitational load is not as going to be as of so much of a concern as your when you would consider the regular structures. Whereas in tensile structures, the uplift, so you have to think about that the tensile structure will get uh, blown away with the wind. So if it gets blown away with the wind, then the behavior of the tensile structure, it's not enough to think about it only gravitationally. You have to think about what will happen to the tensile structure when it moves, or if the wind comes and blows it upwards. Okay, so this is the unique thing about this. In portals also, you have seen that portals also, if it's a cantilever portal, then you have worried about the uplift, because it's a cantilever load. But in tensile structures, all the points, it is not just a cantilever, all the points, you are going to worry about the anchorage more than the support. So it is not the bearing so much. You are not going to be worried about the soil strata and the bearing of the foundation of the support, because the structure itself is very lightweight. In many cases, it might be lesser than the weight of your own weight. But the problem is going to be about it getting enough anchorage. Okay. So um, it needs to be pre-stressed. To prevent that from happening, you need to pre-stress it. Now, pre-stressing is the most common stabilization techniques. It is about application of external force to pull the surface taut, or this is one method, which is the regular tent structure, or pre-stressing can also be done by internal pressurizing of volume enclosing membrane, which are considered to be pneumatic structures. So the diagram below gives you an idea. Hello, somebody wants to say something? Yeah. So the diagram below gives you an idea. The left one, this one is a tent structure. This one is a pneumatic structure. In this, the tension is created, or pre-stressing is done by pulling these cords diagonally in two different directions. Okay. Also, in this cases, you are having something called as a anticlastic surface. So one direction of the curvature is upwards, the other direction of curvature is downwards. With these two opposite kind of curvatures, you are able to have a stable fabric over here. Whereas this structure is synclastic surface. Now this obviously is not, because it is pulled at some corners. It doesn't even have a mast. So what it has instead is the whole volume internally is air pressurized. So you have pneumatic way in which this is kept in place. Now pneumatic structures are of two kinds. They are air supported structures. On the left you have a diagram where it shows that it is a single membrane, and there is air conditioning system, so no air is allowed to escape. So the internal air is at a higher pressure as compared to the external air, and this pressure difference keeps the structure afloat. Okay. Whereas in air inflated structure, it is to be seen like a mattress or a pillow. So this whole thing is a pillow filled up with the mattress. And when you have these inflated structure, you will be able to create. So the internal pressure can be same as the atmospheric pressure. You don't need to worry about. So in this particular case, you have to compulsorily go for completely entropy condition or air conditioned spaces. In this, you can still create open spaces, okay, which have connectivity with the outside, and it will not structurally fail. Okay. Next is about so these are the examples of pneumatic structures. Now in this case, you see very clearly that this ends are sealed off. So the air is not allowed to escape from anywhere. They are all, it is enclosed because it is also giving the pressure inside. Whereas in this case, this is connected, it's like an igloo, it's an inflated igloo, and this is connected, and it is supported by inflation. Now, how do we, as architects, rather than getting into the working of it, the first step would be how would you design using the tensile structures when you want to design tensile structures. There are a few steps which are recommended, not necessarily that they will go always in this sequence, but it, at least for beginning, for when you are starting, it works. And even in practice, it follows a similar kind of process. The first is evolving a suitable form, just like you are conceptualizing the ideas and all that, so sketches and all. The second is you decide what is workable, workable pre-stressing method, whether you want to create pneumatic structure, whether that form requires pneumatic structures, whether it requires a tensile structure in pneumatic, whether it requires inflated structures, or whether it requires a this supported air supported system. Now, most of the time we have experienced that most of the students go for tensile tent-like structures rather than inflated structures. Some of you can choose when you are exploring these structures, you can choose which one you want to do. But even in tent-like structures, you will have to determine whether you have enough number of points, how many points you want. You want a single tent, you have a series of tents joined together. All those kind of things you will have to determine. Now, tent also can be developed out of mast, or they can be developed as we have seen earlier, using anticlastic surfaces. Okay, so whichever form that is workable for you, you got to first explore. It is about exploration of form making, um, deciding what is the workable pre-test methods. Now, third is testing the proposed structure for stability under all loading conditions. Now, this obviously goes in the engineering bit of it. Okay, but the first two stages are where we also use different processes, whether they are using stockings or whether they are using fabrics, whether they are using soap bubbles. So there are different ways in which these suitable forms can be explored. Okay, and it is not just through sketches. So your soap bubble models are photographed, they are analyzed, and then you come up with a most suitable kind of a structure that you want to come up with. The third stage is the engineering stage, where this testing of the proposed structure for stability under all loading conditions is considered. Now, this, at least in our studio, when we ask if somebody is exploring the tensile structure and we make the diagram, we try to incorporate this stage as well. Okay, this is a stage where we discuss with the students with the model they have prepared and try to ideate and help the student understand whether it is stable from all loading conditions. So we will, at least through the discussion, we'll tell you whether this portion will have more load or not, and that's how we arrive at. But technically, if you go in the profession, there are softwares which help you understand these loading conditions also, and there are these demonstration pilot samples which simulate those loading conditions. The fourth part gets into the construction bit of it, where we talk about dimensioning of the parts, both fabric and cables for the manufacturer. Now, please remember that just because it's tensile structure doesn't mean that it is a stretchable structure. Okay, none of the components of these are as good as permanent structures. None of the components have dimensional kind of ability to stretch or alter. Though you will be using stretchable material for model making, but in the real time architectural scope, you will not be using a flexible material. You'll be using very stiff materials. Okay, so the whether it is a PVC fabric or whether it is a HDPE fabric, they are all stiff fabrics, and the parts have to be designed. It just imagine like it is an umbrella, right? The umbrella, the segments of the umbrella are shaped, pre-shaped, and so when you close the umbrella, you will have folds. You won't have the fabric stretching back into one single kind of. It is not an elastic membrane, right? It is a fabric. So similarly over here also, these are going to be fabric. It has to be imagined as fabric, and the parts have specific dimensions. So they have to, a lot of surface development has to be done to arrive at these dimensioning of parts. Okay. Then you have finalizing choice of materials and finishes. So depending on the longevity of the structure, whether it is on the seashore, whether you want to when the structure to be lasting for 1 year, whether it is an exhibition pavilion or whether you want it to last for 25 years or maybe more number of years, you will choose different materials, and obviously it also depends on the budget that you have. Okay, so. Again, I repeat that these need not be linear. Sometimes you get materials and finish, somebody sponsors it, and then you start with these choice of materials. Okay. Sometimes you say that the manufacturer or the person who is with whom you are going to interact with, he has certain limitation of the cutting and welding of the fabrics. I'm calling it welding for a reason. I'll come to later when we discuss the fabrics. But sometimes the manufacturer or the workers determine what is the nature of the form that you're going to get. So it is not necessary that this 5 stages will go linear from 1 to 5. Yeah. Now, how do you decide the surface geometry? So, surface geometry is decided, it is a combination of curvature and pre-stressing. Yeah. It is, you intentionally, deliberately induce curvatures to enable transmission of lateral loads. Okay. Now, pre-stressing ensures the fabric remains in tension and hence stable under variety of non-uniform loads such as wind buffeting or uplift, usually half a ton per meter width of the fabric. Yeah. Now, the diagrams over here, okay, if you look at, uh, if these two are, uh, it has lesser stress and this has more stress. Okay. So obviously this is going to be unstable in this portion. So it will tend to collapse in this direction. Again, if this is longer, okay, as compared to this, again this is going to be unstable in this direction. Yeah. So uh, if you have four corners being pulled, then you have stability induced. Okay. What do we mean by that? Now, okay, look at these diagram. You have point A, point B. Now, if there is point P, and if you don't put this stress, this dark diagram, okay, if that stress is not there, this will tend to straighten out. It will tend to collapse in this direction. Okay. Similarly, if this point C, D, and even if there is a point P, there is a mast over here. And if you don't pull in this direction, it is tending to going to collapse in the other direction. So the way to do it is either I have something which is anchoring over here, or I have a point A and point B diagonally opposite so that it is stable in both the directions. So how do you decide the surface geometry? This is a plan ABCD. Okay. Now, if I keep these diagonals as low and this as high by either introducing a mast over here or pulling it, there are buildings adjacent and I pull this on and anchor this to the buildings adjacent to it. In whichever format, I am able to create these two kinds of surfaces. One is curving upwards, one is curving downwards, and they are acting in opposite directions. That's how I'm going to create a stressed membrane. Okay. Now, the best way to understand synclastic and anticlastic surface is this diagram. If you look at a tire tube, okay, the outer surface of the tire tube, okay, the curvatures are both in a similar direction. So they are synclastic. So the dark area, the white area is synclastic area. The darker portion is the anticlastic surface. Whereas in a dome, you have uniformly a synclastic surface. Okay. Then the common forms, you have hyperbolic paraboloids, which uses anticlastic surfaces. You have double ring cones, also which uses anticlastic surfaces. Okay. Uh, Now, this are also modeled using soap bubbles or fabric, okay, or stockings. This is modeled using soap bubble diagrams or stockings again. But these are the ways, these are the different common forms through and you combine these forms in different ways to arrive at your final architectural form. Okay, so the basic forms were what was shown in the previous slide. The modified forms are these. So this is where you have a series of points being picked up, and you have these hyperbolic paraboloids operating at all these surfaces, and they are coming up with this. Uh, these also, there are ribs introduced in the middle. So these are by the introduction of points through mass, whereas these are through the introduction of ribs. Okay, and between the two ribs, you have anticlastic surfaces which are created. One which is curving in this direction, the other one curving in the other direction. Whereas you have domes which can be lifted up, and again, as in this surface, in this portion, you will have completely synclastic surfaces, but on the lower side where they are anchored down, you will get anticlastic surfaces on the lower side. Yeah. So how do you find forms? So there are different ways. Physical modeling is one, which uses correct shape of stretch fabric, can be found by physical modeling. Now, models can either use soap bubble films, which is seen over here, or thin textiles such as nylon stocking materials. A soap film can be formed within wireframe representation any desired. A film with a uniform surface will define geometry of the full size membrane. Okay, so now this is using the stocking or membrane, whereas this is by using soap bubbles. Swarm finding methods can also be computational. Nowadays, we use a lot of computational tools. We'll come to which are the websites which give you simple forms, but there are advanced modeling tools also in structural engineering which allows you to do that. Yeah, but that itself is in fact, this particular topic is a full-fledged one-year master's program. Okay, in tensile structures. Okay, so the topic is very vast, so we are just covering the introduction to the topic. Yeah. uh, in computation method, you have force density methods and dynamic relaxation techniques, which are most commonly used. The computer finds a form that a pure membrane would assume if stretched between the proposed boundaries with uniform tension in all directions. Later on, all the properties such as physical characteristics of proposed membrane, supports conditions, positions, edge sag are altered to get desired geometry. Okay. Now, computational forms are, you have again the same thing what you have done in physical, you do it in computational also. So if you use Rhino or any of the ArchiCAD or these tools, you will be able to do this. In Rhino, you will be able to do this very easily. You have initial boundary conditions. I think in SketchUp also you are able to do. I'm not very sure, but I think you are able to do this in SketchUp as well. Yeah. So any of the 3D modeling software, you should be able to do these basic forms. Okay. Um, so uh, in now, if you look at the basic form, these are the points that are created. This is creating the outline. Okay. Now, if you look at if you introduce a mesh inside, you will have different kinds of meshes. Okay, the rectangular mesh generation, the actual edge has been recalculated based on the optimized surface shape and the prescribed edge sag. Okay, so now in this you will have these very closely spaced, whereas this is stretch. Okay, and this is also used in the real time scenario also. If you use these this as cables, or these as ropes, and you intertwine them, and if it is a rectangular piece and you just twist the rectangular frame, you will get these various hyperbolic paraboloids. Yeah, so the same thing is used in computational modeling also. But if you use only the outline, then obviously you're not going to get, you will have to introduce the mesh inside to be able to come up with the shape. Yeah. So changing the edge sag and changing high points. So the edge sag can be changed, or you can also change the high points. Yeah. Should I pause here a bit and check what the questions are, if there are any? Full screen mode as well. Okay. I'm not able to see any. There are no
No,
patents.
there are not. There are not too many. There's,
Okay, I'll continue.
could we see the cursor? That's all. Nothing.
Okay.
Nothing as of now.
Yeah, okay. Thanks. So then we come to what are the materials that membrane structure uses. Membrane structure uses largely the materials which are used can be categorized into three ones. One is the woven fabric, which is the traditional. The tents were created when, just like a cloth, you have fabrics which are used. Now, only over a period of time, instead of cotton fabrics and cotton as a material or jute as a material, you have different plastic fibers which have come up. So you have PVC coated polyester, you have Teflon coated glass fiber, or you have silicon coated glass fiber. Okay, they all have, I mean, we'll come to anisotropic behavior. But second category is films, which is like homogeneous sheets of plastic or rubber. They are highly flexible and isotropic. uh, okay, they are weaker, less durable, and less tear resistant. I'm not sure about that. There are many fabric which claim that they have much higher longevity, and they have much better this. But yes, tear resistance, woven fabrics are much more resistant to tear as compared to films. Films, if you, because they are under stress and you just puncture one point, the tear is going to reflect all over. It's just like taking up your plastic sheet. If it starts tearing at one point, it will. You are sure that it will tear throughout the end. Unlike the fabrics where even if there is a puncture, the other fabrics will still hold true. Okay. The other ones are reinforced films. So it is a combination of fabric and films where the plastic or rubber film is reinforced. So if you go into the market and if you have seen these tarpaulins, which is plastic sheets, there are black plastic sheets which are continuous. So they are almost like films. They are homogeneous sheets of plastic. Whereas if you look at blue plastic carefully, very closely, they will have these fiber reinforcement within it. So they are composite of fabric and film structures. Okay. Whereas woven fabrics are conventional. What you use in cement bags, the modern day cement bags is also a woven fabric. Yeah. Now, what are the characteristics which are desirable? If for short-term structural properties, you have long-term structural properties, and you have non-structural properties. So for short-term, you want tensile structure. Now, in most of the cases, you will find that PTFE. What is PTFE now? Going back to this slide, it is Teflon coated uh, fiberglass. Okay. Now PTFE has much more tensile strength as compared to PVC. Even the tensile modulus PTFE is has much higher. Tear resistance also PTFE is going to be much higher, better. In terms of directionality, eh, that means the in which direction it can be oriented. They both the same. In long-term structural properties, construction stretch, PVC is better than PTFE because PTFE is a little more stiffer as compared to PVC. In terms of dimensional stability, because the PTFE is stable, it is stiffer, it will be more dimensionally stable as compared to PVC. In non-structural properties, you have durability and you have translucency. Now, durability is the one where PVC PVC has a life expectancy of 15 years and PTFE has a life expectancy of 25 years. Of course, this is a very old slide. Now with the industry, there are people who are, there are industry, there are products which give a better life also. Translucency is very important because most of these fabric structures, if they are exposed to the sun and they are exposed to the UV radiations, then they are going to yellow. So this is very important from our point of view, because many of these structures, they look very ugly when this factor is not considered. Okay. Uh, Translucency also is about whether it will allow some kind of light to enter inside the structure. So if you look at PVC, they will allow almost 38 to 30% of the light, whereas PTFE is lot more stiffer. Being stiffer, they will not allow so much of light. Fabric joints, uh, you have different ways in which the joints fabrics can be joined. There are sewn joints, there are heat welded joints, and there are mechanical joints. Mechanical. So sewn joints are they are strong, but thread is susceptible to degradation. So you have to pay attention to what kind of thread you are using also. They are ideal for PVC but not suitable for PTFE. Okay. Heat welded joints, their heating can be done by jet or hot air or radio frequency electromagnetic radiations. They are suitable for both PVC as well as PTFE. Mechanical joints, these joints are required along with about to for actual execution on the site. They use, we'll come to that, using aluminum clap planes, or they are using extruded aluminum luff groove strips. These are the mechanical joints. Now, in between the fabric, you can have the other two, the welded or sewn joints. But when it comes to connecting them to the cables and where the maximum stresses are coming, where you are anchoring it back to the ground or you are anchoring it to the mast, that is where your mechanical joints become important. Now, the mechanical joints, when two, fabrics, and even the mechanical joint helps in the assembly on the site also. So when two fabrics are joined, please observe this very carefully. I can, yeah. So one fabric comes over here, it rotates around the bolt rope. Now this is going to be pulled in this direction, and this membrane is going to be pulled in the other direction. Yeah. So this fabric is coming around over here, and it is stretching in this direction. Yeah. And in between you have two additional strips which are going to give a friction, or it is going to have a it is going to have a some kind of a stiffness which will allow so that this doesn't slip off, these fabrics don't slip off against each other. Yeah. Now above that, to prevent this from coming from shifting on this side, this is it, huh? Adi, तो शटर बंद कर. You have these aluminum clamp plates, which is clamping both the ropes together, and it will not allow the rope to come in either direction, so it will anchor it firmly. And these clamp plates are fixed with the help of bolts. Okay, they are stainless steel. The other way of doing it is the membrane is wrapped around this cable. Okay, and or it is there is a this bolt rope itself has a certain clamping mechanism with which the membrane is going to be clamped. Now this detailing is not shown over here. Yeah. So once that is done and you have this rope, you just slip this bolt rope into this luff groove strip. Okay. So you can do this, or you can do this. This will be patented. This will be customized. Whereas this will you can do it using all the parts which are available in the market. Yeah. Then you have the cables themselves. Okay, tendon types. Okay. Now tendons can be a simple high tensile rod. It can be a compact strand which is using uh, different varieties of shapes of smaller cords. Okay, so these are smaller cords These are other not circular shape, and there is a circular shape cord. So there is a diform compact strand. You can have multiple strands of all uniform dimensions, or you can have bunches of strands again clubbed together. Okay, so now on how it behaves, the axial stiffness, the tensile rod obviously is high, and this is low. Flexural stiffness also, this is very high, it's very stiff, and strand is low. Tensile strength, uh, this is said to be high, this is low. Now, many a times you don't want very stiff um, structure. So because more the stiffness, you are going to have problem about the shape is not going to be smooth enough. So you will prefer these bunch strands. Many a times your flexural stiffness also is going to be a bother. So you're going to prefer this. But in terms of high strength, tensile strength, you want to tend towards it. So depending on what your requirements are, you might go for any of the four option possibilities. Now the materials that you may use is you can use stainless steel, you can use nitronic 50 steel, or you can use galvanized steel. They are all available for solid rods as well as spun cables. Diameter range will be anywhere between 4 mm to 35 mm for solid rods. It will be anywhere between 3 mm to 19 mm for spun cables. Now, those were the cables themselves. What about the terminations? The termination, because they have to anchor, they have to be fixed. Cables, obviously, you are not going to. It's not like ropes that you can tie easily. So there are terminations for these cables. Now, terminations of these cables are, you can have fixed length tendons where the eye and the pin, okay, they are they are rigid, they are fixed, so there is nothing you can adjust about this. You can have adjustable, so these ones are used at the ends over here. Okay, the second ones, the B type, is where there is a turnbuckle, a threaded stud, okay, which are used somewhere over here. So these threaded studs are used where to adjust. Okay, you can have a combination of this. So this is over here where the pin, the fork, as well as the adjustable length tendon is over here itself. So you don't have to use these in combination. So wherever you're using this, you might have to use a combination of this, but this itself is good enough. This offers a little more flexibility where the tendon, the adjustment as is at the center and not at the termination. So it is a singular unit. Yeah. So you have fixed versus adjustable. The method of adjustment depending on that, and the tendon length and diameter. These are the concerns that you need to bear in mind. So you cannot have something which is very close to the ground, so that even this cannot be adjusted. So you need to leave enough space to accommodate these tendon terminations. Yeah. Now this is one of my favorites, which is because it uses timber, it uses steel, it uses fabric as well as the cable. And look at the elegance of this. It is just supported on the central shaft. This otherwise this is not coming into any picture. So this is supported on these three columns, three masts, and these three masts with this ring on top, and these things, they are supporting this structure. Fabric used is Velcrane, ones that are used for yachts. And now I must tell you that a lot of tensile structure understanding comes from either sailing, or if you are going for treks, or if you are into if you understand tents. So if you have a mobile kind of way of living, your understanding of tensile structures will be much better. Okay, so that is where traditionally it has been used. There is, if you look at all the camp and the tent equipments and gears, there is a lot of development on that front also. So tents ranging from 16 people tent to larger tents, also are being used for campings, and also sails, because on the sea sails are very Adi, please, you can cut, but don't do that. Sorry. So now, uh, in this particular structure, this they have used yacht sails, and they have joined these fabric has been joined using radio frequency welding. Mast and booms are made out of laminated timber with oval cross sections, and there are stainless steel spice plates for cable attachments. Yeah, these are the plans, how this is done. There is a coat hanger structure which is done over there, and then after the coat hangers shape is placed over there, then the rest is stretched downwards. Yeah, and this is the skeleton. So all these are timber. They are engineered timber. Okay, and the joineries are stainless steel, and the rest is all fabric. Some more uh, photographs and images, drawings of this, of how this shape is achieved. It's just these two posts. This post continues in both the direction, and they are pulled back so that they remain in place, and the rest of the all the hangers are suspended from this cable in between. Yeah, and look at the images of this joinery also. So the timber, there is this plate and there is stainless steel kind of thing, that the pin, the connection which is designed over here. If you look at it, the stainless steel has gone inside and there are bolt joints over here. So there is this plate which is entering deep inside, and it is getting bolted to the timber, so that there is no splitting of timber. Okay, and there is a firm joint over there. So all these joineries become very critical in the tensile structures. Yeah, yeah, Jimmy, it's not such a long presentation, so we are almost done. So these are three useful websites. um, if you membrane24.com, it's a very useful site where I am taking a lot of time. Anyway, so yeah, so anyway, you can explore these. There would be other sites also which which have recently been added, but these sites help you to shape your parts, different parts of the fabric also. It helps you in generating basic forms. These are not advanced. These are mostly promoted by a manufacturer or vendor. So it will be limited by what the vendor or a manufacturer is capable of doing. Okay. So if you want to specialize in this field, uh, there are programs which are 1 year programs, which of course there's a lot of engineering on that front, but there are many of them, many programs on that. Yeah. So with that, I open the floor for questions or any reactions. If the film fabric are less durable and less resistant, why is it used? No, it is relative. But film fabrics are also, it is about, first of all, film fabric. Sometimes you want, if particularly if it is a temporary structure, you want a flexibility, slight adjustment as per site conditions and all. And also film fabrics become cheaper. They become cheaper to replace also. So many a times you tend to go for film fabrics. Okay, but the common thing nowadays, because for example, if we had this in the college itself, we had a workshop long time back where Ferrari fabrics were promoting it, they had come up with a film which was very tough. So it was not reinforced. It was a regular film only, but it was very tough. Uh, Second advantage of film is it is less prone to leakages. Okay, because it is a continuous, it is a isotropic surface. Uh, Sorry, what did I say? Yeah. So the surface doesn't allow any water to percolate in or to come out. So whereas in the woven fabric structures or in other PTFE membrane and all, if the in between the membrane of it, if it starts uh, wearing off, then there is a possibility of, so you will see it in your raincoats also, right? So in the raincoats, the film which is preventing the moisture from coming in is what the coating, the Teflon coating which is there on your raincoats. But if you go for a plastic raincoat, it will tear very easily. Okay, but then you have these very good raincoats or jackets which are woven fabrics on which there is film which is coated. So most of the time, even in architecture, you use a combination of the two. So the composites are more popular these days. Does that answer your question, Somil? Okay. Any other questions? What is radio frequency welding? uh, do we get cleaner joints? Okay, see, uh, this, if you go for conventional caravan tent which was made out of canvas, obviously we are not going to talk about welding. Okay? We are going to talk about stitching. The old army tents and all, they were all stitched tents. Okay, but with the with the uh, plastics coming in, plastic industry coming in, with the PVC and PTFE coming in, the this plastics can be modulated or maneuvered using heat, and this property of the plastics is used to fuse them together, and that is where you got to welding comes into picture. So it is not welding in terms of steel welding, but it is how you fuse plastics together. Now, plastics, when you, if you use heat welding, your precisions, your accuracy, or the temperatures might slip further, and it will compromise on the strength of the membrane itself. So that's where your radio, because radio frequencies also generate a certain amount of heat. Radio frequencies, uh, when they are, when the fabrics are sandwiched in between and radio frequencies are passed, they will activate the play. It is similar to using your microwave. Yeah. So these microwaves, the radio frequencies will heat up the membrane, and it will allow it, the membrane to be to fuse, to get some time to fuse, and that's how they will get welded. And because they are plastics and they fuse together, they will also form waterproof surfaces. Okay. How are rainwater harvesting systems incorporated in them? Okay. Rainwater systems, there are these, I don't have that image, but I'll try to locate that and show it to you. There are these water barriers at the ends. Okay. Now, these water barriers, they are slightly bulged portion at the end. Uh, and these bulged portion, yes, yes, yes. Hello?
No, Vikram, your initial three slides has that inverted, like the way we have at our domestic airport.
Okay, okay. I'll just go back to that.
Just right up.
Thanks.
It's, I think, just Somil's question, no? Somil, you
Yeah.
must, yeah. This particular typology, that one, back one, slide above,
Which one?
slide above,
Slide above.
next, yeah, next slide. Yeah, this particular typology. where the center,
Ah, but this is
not
there
this
are
one, above one,
even
above one, above one.
this one. Now this is the shape
No,
itself is allowing
uh,
to.
Vikram, the earlier slide. Even this, to a certain extent, will allow, but
Yeah.
this one, it's in the center. The usually the support system also works.
Mm.
The central
Now,
support
not
system.
only that, Soumya, this in fact is very useful for diverting all your water through this post. So all the water that you're catching, you're directing it through a center space. But even otherwise, in the tent structures also, there is a way of there are water barriers that you keep at the edges, and that will direct water. Like for example, in this structure, okay, at this joints and even at the edge, this edge will not allow the water to drip like this. Okay, there is the cable over here will divert the water from here to here on this sides. Okay, so there are these very subtle kind of details which help the water to be directed, channelized towards to where you want and not spill over on all the surfaces. So once they are channelized, then they can be collected through the pipes or through whatever design mechanisms that you have, whether it is passing through these columns and all, and then they can be taken to the harvesting systems. Yeah. Anything else? Does that answer, Sawmill? But I'll try to locate the section detail also.
I like to add that other than planning for large structures in tensile, uh, which really which at times become difficult to convince a client considering the technology, the availability of the material, in some sense that the permanence of the tensile structures are a big hit in conservation sites. Yeah, you have to understand that when you do people who are dealing with historic sites, people who are dealing with inserts where you want the structural footprint not to be permanent, to have the idea of temporality, the idea that it is made in a contemporary material, looks lightweight, is dismantlable easily, then though usually we don't go about building structures and dismantling them after a week or two, yeah, but the idea that there is something that can be built so lightweight that it doesn't so it so even visually it doesn't occupy that kind of that mind in the mind that you have built something out of brick and stone in on a site which actually you were not very keen to intervene. Yeah, when you especially we intend to take a lecture when the college starts on heritage and historic sites, and that time we will see how materials and technologies such as these, which can be put up, have the notion of it being temporal, be lightweight. As you know, as you all know, most tensile structure, most fabric structures are white, so they add to the lightweightness of the when you build transitional kind of programs in and around, they can be historic monuments. Just imagine you have a historic monument. You may need to make a ticketing center. You need to make waiting areas, queued areas. In such areas, linear and in the linear typology, the tensile structures work wonderfully well. Other than but naturally spanning having large spans and being lightweight in nature. So not only is the typology being used more frequently now, considering we are intervening more in historic districts ever more than earlier, but we have seen all across. Like I did a project along the highway, along the Western Express Highway, and there is something called as the highway expansion, yeah, that does not allow you to build for quite some distance at the side of the highway, saying that in the near future the highways need to widen. At that point of time, the only way to convince the authorities that the structure that we are building is completely temporal. It only has some very lightweight foundations that can get submerged once the road expansion takes place. But other than that, the column systems, the support systems, and the roof is all very lightweight. Yeah, it's as good as I could have convinced the same using metal roofs and trusses that also could be dismantled. But a tensile structure can equally be justified as to be uh, dismantlable and lightweight in nature.
Jimmy, to add to that, there are see in conservation there is a maxim or ethics which talks about reversibility of whatever you're doing. So tensile structures have become significant from that perspective, because whatever intervention you do, you can dismantle it and take it away. So that's what Jimmy was explaining. So it aligns with the philosophy of conservation. And also many a times in Bombay you see, if you look at even Antilla during the monsoons, with you are very. I'm sure everybody is remembers that image of blue tarpaulin all over, okay, across Antilla. Imagine if the architect himself would have designed something which takes care of the monsoon using the fabric structure, okay, tensile structure. It would have been so much of, so it would have made such a lot of difference other than having so there is a lot of potential to use tensile structures and tensile material in different contexts, particularly in our case where monsoons are they are 3 months in a season, and even the government allows temporary structures to be erected for weather protection. Yeah. Yeah. Any other questions?
Sandhya, madam, you are there. Would you like to add something? I see she's there.
Is she?
Yeah, yeah.
Yeah, I'm there. I'm listening to what you're saying.
Would you like to add something based on your experience?
No, 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 nothing.
Okay.
Madam, have we covered with this class Sidco Exhibition Center? Can this class confirm? Were they taken to the Sidco Exhibition Center? Today it's being used extensively as a quarantine center for New Mumbai. I do not know. Yes, people said they have been taken. Okay, otherwise I was keen to take the keen to introduce them to the uh, roofing
They have
systems.
been, I think they have gone to for a site visit there.
Yes, yes. The students have confirmed. Yes, yes, yes. Okay. Otherwise, I was keen to introduce the subject of space enclosures using the kind of uh,
Yeah, but
spanning
when they
system.
went, they just looked at it. They didn't analyze it, and then they enjoyed their
Fine,
going there.
Photographs, so they would try to
fine.
अभी तो possible नहीं रहेगा with the quarantine center.
No, not about going. It is about using. It is
Yeah.
about it is how you use a certain structure to analyze, because we have now some topics on space frames and girder systems and shells. So Vikram, between myself and you, we have, and then Sandhya madam could perhaps work with a presentation on auditorium. So we have another 3-4 classes. We have to discuss how we take it ahead. But I don't see any query other than sawmill. I don't know whether the others.
Are they
Uh,
sleeping?
I don't know.
None
That is
of
for
the,
them.
none of the students are they have not thought about using tensile structures ever, or in their designs. I'm sure that people must have worked with tensile in the earlier classes, at least conceptually in your first year, second year. I'm sure you would have done that.
Whatever, whatever. Yeah, it's nice you wound it up in an hour. Otherwise, it becomes
I
difficult. Yeah, tension.
Wasn't Devesh supposed to take this?
No, no,
No.
no, madam. Devesh usually takes, if we can request Devesh, he usually takes enveloping systems and new materials for enveloping systems. He has a presentation that we can always request him if he can take a class.
Yeah. Okay.
This was
Or
used.
else,
This was
or
originally
else
used to be taken.
when college reopens.
Sandhya, it
Yeah.
was taken by Saumitra a long time back. This
Yeah,
topic.
yeah.
Yeah. Yeah. Yeah. Yeah. Yeah.
Okay. Anything else?
No, I don't think they are.
So we can call it a day then. If there are no questions.
Chalo.
Okay.
Okay. Bye.
Bye. Bye.
Bye, Vikram. Thanks.
We have openings in tensile structure. How do we arrest water? Okay. We can have openings in tensile structures. We can have skylights also, dome skylights also. And the arresting water will be the same problem. You have to geometrically figure out what is the alignment of your skylight so that the water doesn't get trapped on that and it is allowed to run on the surface towards the end where you want it to. Okay, thanks.
Tomorrow I'll take diaphragm walls. Yeah,
Okay. Yeah.
yeah, yeah,
For the fourth year.
yeah, for the fourth year. Yeah,
Okay.
and then how we intend to take it further by way of high rise and uh, high rise and
Finished files and all.
Aji. Yes, yes, yes.
Files वगैरह.
Piles, basements,
Placements we have finished.
piles, basements, soil, all of that is covered by Vikram. Vikram, you said, can you take? You took the attendance again at the end of it? No, forgot.
No, no. Yes, yes, yes.
Just take that, and more important is that shut the recording.
Just a second. I'll have to shut the recording. Yeah. Recording.